you get closer to the house and you focus on one angle, then you might be able to get more details like the materials of the door, the windows, some decoration, and so on. All right. So that's the idea here. Okay. So we want to be able to extract. We want to be able to get specific local features in specific region. All right. Now let us look at more concrete examples. Okay, let's consider this image. Is an image of 5, as you can see here. All right. Where the black is equal to 0 and y equals to 1, just to simplify the discussion. Let's say we want to build a system which can recognize this image is a digit of 5, right? Now, if we have the image on the right, let's say, image on the right, okay, still we want the system to be able to recognize it, although the image is distorted or deformed or corrupted, right? Now, if the system, you might think, oh, we could somehow use a pixel by pixel comparison. If the system use that approach, then the system might fail because the arrangement of the pixels are not the same, right? And now, so how do we build? The question is now, how do we build a system that is intelligent enough to recognize this image? So if you think about how we recognize the image, we as a human beings, uh, we are able to recognize it, although the image is distorted. Okay, why? Because we are not comparing pixel by pixel, right? We are not comparing that to that details. Like, we look at the pixels and we compare it with the image that we want to recognize. No, we are not doing that, but we are looking for, I would say, might be the pattern, the shape of the entity that we want to recognize. So, but in this case specifically, basically we are looking at the features, okay, characteristic of the entity. In this case, the features of the digit. Okay, if the features exist, for example, let's say the features that we somehow recognize we have in our brain occurs or exists in the data, then we can conclude that there is the entity. In this case, this is the digit of 5. So what would be the feature? For example, let's say if we have these 3 features, right? Feature 1 is a corner, as you can see, is a corner, right? This is a feature 1, and this is another corner, feature 2. We can say corner 2, okay? And this is a horizontal line, for example, let's say simple features, okay? Just for the sake of discussion, right? So if we, let's say, if we are given this image, the corrupted one or new data, right? So we look for that features, the same features that we have, that we know, that we basically encode that if these features available exist, then we can conclude that this is a digit of 5. So given this new corrupted image, new data, so we can see that we have the same features. Okay, we have the same feature, feature 1, feature 2, and feature 3. So these are the features. So if the features available exist, then we can conclude that this is a digit of 5. Then the system is more intelligent. All right, system is more intelligent. Okay, now, so what are these, features? Features, as you know, is just a mini image. So it's just a mini image. In this case, the feature one is just 110, 110, 111. And feature 2, as you can see there, 111, 001, 001. And also for feature 3, we have 000, 111, 111, right? So how do we pick up these features? How do we know, okay? How do we basically detect, these features, right? So as you can see, in the corrupted image we have on the right, we also have the same features, right? And those features are represented by the same set of values, right? So how do we pick up these features? We can apply filter operation. Okay, we borrow the concept in image processing, filtering operation. For example, let's say in order to pick up this, feature 1, okay, the filter might be 110, 210, 211. right? For feature 2, okay, the filter might be 122, 002, 001, and so on. Also for feature 3, we have a specific or specific set of filter values. You might ask, like, how do I get this filter? Okay, so I made up the filter, all right, just for the sake of explanation. Later on, we discuss how, in the context of neural network, how do we set this, how do we get the filter values? All right, now, so if we have these filters, okay, so filter 1 should be able to pick up to detect feature 1. Filter 2 should be able to detect feature 2. And the next filter, the last filter, should be able to, detect feature 3, right? Feature 3. Okay, so how do we apply this filter, okay, on the data so that we can somehow get, get an output, something that we know that, this feature is available, all right? Okay, so assuming that we have this, okay, we have input here, all right? So the input consists of 4 by 4 pixels, all right? And the pixels are A, B, C, D, E, F, G until P. And we have a filter 3 by 3, as you can see here. This is a 3 by 3, and this is 4 by 4. And the filter values are R, S, T until Z, right? To apply the filter on the data, okay, the operation is very simple, as you can see here. So we just multiply the elements in the input, right, with the elements in the filter. Since the filter is a 3 by 3, so then we're gonna define a region of 3 by 3, as you can see here, 3 by 3, all right? So then we multiply the elements. So A times R, B times S, C times T, until K times Z. And then we just take the summation, okay? Take the summation of the multiplication. So this is what we call as a convolution operation. Right? Convolution operation. Convolution operation is an operation that preserves the spatial relationship between pixels. Okay, because we multiply, the filter value, okay, with this corresponding element in the data. All right. So that's basically convolution operation. Now let us use this, the example. So we have the filter just now. This is a filter 1, right? Okay, so we have filter 1 is indicated by the black box. And then we have the feature, okay, indicated by the green box. All right. So the convolution operation is, the calculation is just 1 times 1. All right. So did we get 1? All right. And then 1 times 1, the second value, times with this, the second value, second element in the region, 1 times 1 again, and then 0 times 0, 1 times 2, 1 times 1, 0 times 0, until 1 times 1. And then we sum them all. Okay, we get an output. So this output indicates whether the feature is, there or not. All right. Okay, now let us apply, okay, this filter to the whole pixels. All right, so this is just one region in this region, right? So let us see what happens if we apply the filter across the pixels. Okay, now, so here we have filter 1, all right? Filter 1 when we apply to the image, all right? So these are the output, as you can see there, the output of the convolution operation across the whole image, right? So this is when we apply filter 2, okay? And this is when we apply filter 3, right? Filter 3. Now, what can you notice from the output? So we have just basically, of course, the output is just, a set of values, right? A set of values. So the values, okay, in the context of neural network, we call it feature map, right? Feature map. Now, as you can see, when we apply the filter, okay, filter 1 to the image, right? So we have somehow a high response on this region. As you can see, the response are 9. Compared to the other regions, we have a smaller response like, we have 7, 3, okay? We have somehow quite a high response here, but still relatively lower compared to the corner, okay, the feature, okay, the region where the feature exists, right? So we have a lower response in the other region, as you can see. So we have a high response here. So that means we can conclude that filter 1 able to detect this particular feature. Now, for when we apply filter 2, we have a high response in this region, okay, which is the second feature, and we have a lower responses in other region. Okay, we have 1, 2, as you can see. In fact, we have 0, okay, which is basically no response, right? And filter 3, as you can see, we have a good response, high response when it comes to the horizontal lines, right? So we have high response here, high response, and another high response. So we the filter able to pick up the horizontal line features. All right. So that's basically how, okay, basically how convolution, able to pick up how convolution works and able to pick up the features. All right. So if you have any question, you can just let me know. You can turn on your microphone or you can just put it in the chat box. All right. So this is the basic mechanism of convolution. Okay, now. So to give you some more ideas what convolution can do, right? So this is an example of using real image, right? So this is quite popular image, right? In image processing. Okay, so we have these filters, right? Filter 1 is the Laplacian filter. The second one, so this is a Sobel filter, all right? So this is a Laplacian. Okay, and this is a sharpen filter. Okay, sharpen filter. Now, as you can see, all right, so when we apply the the filter, okay, the first two filters are basically to detect edges, right? So as you can see, when we apply the filters, we are able to pick up the edges, right? The edges of the data, all right? And the second one is also an edge detection filter, able to pick up the edges, although as you can see, the filter miss some of the edges here, right? And also the tripod. Okay, but still, the the filter able to pick up those, the edges. And the last one, this is a sharpening, okay, to sharpen the, the data, all right? So this is convolution, all right? Convolution. Okay, now, using the same principle, okay, let us translate the same principle to the principles of feature assertion using convolution to neural networks. Right. Now, to predict an image, right, instead of processing the whole data at once, like in fully connected neural networks, we want to process a region of pixels at a time, right? So that we can pick up, we can extract and leverage local features, specific features in that region, right? So that we can get the details, right? So let's say the region is 3 by 3. Okay, let's say the region is 3 by 3. Okay, so we define a region 3 by 3, as you can see here. So those are the input neurons, right? So those are the input neurons, right? Now then we connect, okay, these input neurons, right? We are connected to a neuron in the hidden layer. So here, this is the hidden layer, right? The hidden layer. So these are the input layer. So we're gonna connect these, input neurons or the input data, just not all, just a few. Okay, in this case, a 3 by 3, so 9 pixels, 9 input pixels. And we connect it to this particular neuron, okay, this neuron, this unit in the hidden layer, right? And we know that, okay, each connection has a weight, right? So this is a neural network. So we have a weight here. So we have W11, right? So we have W12 and then W113, right? So, and then we have W21, W22, W23, W31, W32, and W333. Okay, so these are the weights, okay, of the connection, okay, associated with the inputs, right? Now, so these are basically the filter, So the filter is basically just the weights of the connection, the weights of the connection. Okay. So, and of course, these weights, as we know, okay, in neural network, you are not going to define the weights, okay, but we are going to train the weights. Okay, we're going to train the weights by using gradient descent. Okay, gradient descent algorithm. So you don't have to worry how to get the weights, okay, in order to to detect the features. Okay, that suppose, I mean, like that we should be detecting, or we should be extracting from the data, right? So we just train the weights by using gradient descent. Okay, then so this is just the first region. So we're gonna apply the same principle across the whole input pixels. All right. So to do this, we're gonna slide. Okay, we slide the filter, okay, to the right for a certain number of pixels. So in this case, we we go to this region. So that means we skip one column. Okay, one column pixel, right? Using the same set of weights, not a different set of weights. Okay, not different weights, the same set of weights. Okay, so but you can think of it like we apply this this weight on many regions in the input data, because we're going to use the same set of weights, right? So because that's why in this indicated by the blue box. Okay, I use blue box, so that means it's the same filter. We just slide it to the right. Okay, and then we do the same. Okay, we go downward by one, and we slide it until we reach to the bottom right corner of the data. We cover the whole pixels, right? So in this way, as you can see, right, first, we should be able to extract details in the from the data, because we just focus on specific region, right? So this allows us to leverage some details, some information in that region. Okay, we call it local features. And another thing is that because we, as you can see, because we use the same set of weights, right? We use the same set of weights, so we can reduce the number of weights significantly, right? Because in this case, we just have 9 weights to process the data, right? So we can reduce the number of weights significantly, all right? Okay, so that's basically the concept of feature extraction using convolution. All right, now, any question? If you have any question, just let me know. Ada soalan ke?
Still not yet, Doctor.
Okay, all right. Okay, so we move on to the next one. All right. So now we're gonna look at the the neural network. Okay, that this neural network capitalize the special structure that is inherent in the in image data by using the same set of weights, okay, performing the convolution operation to extract local features, right? Okay, now a CNN, okay, or convolutional neural network, like I say, is a specialized architecture. Why? Because first it has this, convolutional layer. So it has this convolutional layer to extract features by applying filters, right, to extract local features. And then of course we can apply the nonlinearity, okay, to the convolution layer to introduce nonlinearities to the model, right? So otherwise your model is just a linear model, right? So in order to make it nonlinear, all right, so we apply activation function, all right? And then we have this pooling layer, all right? So this pooling layer is just to reduce the output dimension, okay, the dimension of the feature map. Later we see why we want to reduce it, okay? And then lastly, we have the fully connected layer, right? Fully connected layer to predict the data, to perform the prediction. So this is in general, right? In general, of course, now the state of the art, we don't have sometimes, the popular network, the popular models, we don't have these fully connected layers. Only, we don't have hidden fully connected layers. We have only output layer, which is a fully connected, all right? Okay, but we are not going to discuss that. Okay, so we have these three layers, right? Three layers. Now, the training of the model is similar to the traditional neural network, right? We want to find the optimal weights of the model, including the filter weights. Okay, the weights, the filter values, right? Those are just the weights, okay, the weights of the connection. So the goal of the training is to find the optimal weights, or you can think of it like the optimal filters that can extract the best local features from the data, okay, for the prediction. All right. So basically, the idea is that we are not going to determine what are the features to be extracted. Okay. So we let the gradient descent, okay, gradient descent to extract the optimal, the most effective features for the prediction, because the weights are determined by the gradient descent algorithm, right? So we are not going to determine what are the best features. Let's say if you want to classify a car from a truck, for example, let's say. So if we think about how we distinguish between these two vehicles, it could be the number of tires, the shape, the size, right? What else? Some of the characteristics of the vehicles. So those are the features that we gonna use to disclassify as a human being, to classify between car and truck. But deep learning, okay, convolutional neural network, we are not going to determine, we are not going to tell, right? So CNN, so you should extract these features. No. Okay, so we let the algorithm to decide what are the best features, okay, to extract for the prediction. All right. Okay, and so that's about the weights of the filters. Okay, so the weights of the convolution layers will be trained by the algorithm, and similarly for the fully connected layer, right? Fully connected layer. So we are not going to decide. This is like the the traditional neural network, where we let the algorithm to determine what is the best weights for the fully connected layers for the prediction. Okay. Now, let us look at the parameters of the convolution layers. So you have to know the parameters, okay, in order to to build a network, either using TensorFlow or PyTorch, because you have to define the parameters. All right. Okay. Now the first parameter that you have to set is the filter size or the kernel size. Okay, the kernel size or the filter size, they are referring to the same thing. Okay, filter or kernel. Right. So the size is basically just the height and the width of the filter. It defines the size. It defines, the filter size defines the size of the region for the convolution operation. Okay, when you want to process, okay, when you want to process the data, remember the the region that we have. We define the region. Okay, So the region is determined by the size of the region determined by the filter size. If the filter size is 3 by 3, then we're going to look at just 3 by 3 pixels, right? If it is 5 by 5, then it's 5 by 5 pixels. Okay. Typically, the shape of the filter is square. Okay, in computer vision, normally it's square, right? And the number of is an odd numbers. It's odd number so that we can have the center of the we can have that is a center. Okay, we can have the center of the filter or the region, right? So normally we use 3 by 3 or 5 by 5 or 7 by 7. Okay, but theoretically you can decide, you can set your own size like 2 by 2 if you want, or 4 by 4, right? But it's just that, in the literature normally we use odd numbers, right? And it is a square. The kernel is square. And not necessarily, I mean, like you have to be, it has to be square. If you want, you can just, set it like this. It's a 1 by 3, or this is a 3 by 1, right? And this is not rectangle, I'm not sure. Okay, but it's just like the horizon, the column only. Okay, you can think of it like that. But this is typical for time series data. Time series data, like, if you have signals, like signals. Okay, normally we use 1 by 3 or 1 by 5. I've never come across, a filter like this shape. Okay, where it's a 3 by 1. Okay, normally it's either square or like this one for time series data. Okay, now, but another thing that you have to know is that the shape defines the output dimension of the layer. Okay, the shape. All right, so when the convolution operation is applied, it begins, okay, like we discussed, okay, in the previous section, we begin from the top left corner until we reach the bottom right corner. So in this case, the output dimension is 3 by 3, okay, 3 by 3, as you can see here, right? And the filter size is 3 by 3, okay, the input size, okay, the input dimension is 5 by 5, right? Now, when we apply the filter, okay, when we apply the convolution operation, so first we apply here. So this is the center, and then we slide it to the right. Okay, so then this is the center, and this is the last region at the first row. Okay, on the top row. Okay, then we slide it down. Okay, we have this computation, another computation, another one, until we reach this one. Okay, so we have 9 only, 9 computation, 9 convolution operations. So that's why we have the feature map size is, okay, the feature map dimension is 3 by 3, right? Using 3 by 3 filter. Okay, so normally if you apply the convolution operation, the output dimension is smaller than the input dimension, right? Okay, now another thing is that here, as you can see, when we apply the convolution, the first region here, this is the first region, right? The corner pixels, as you can see, the corner pixels, so these are the corner pixels, right? So these are the corner pixels. They are processed only once, okay, only once. So because of that, okay, because they just, we apply, okay, they get to be processed only once, okay, we might lose some information, okay, or we call it an age effect, right? So in order to overcome it, okay, we can use padding, okay, to avoid this, information loss or age effect. We pad the input with extra pixels, okay, and that pixels normally is a 0 pixels around the input data, like in this case. So the 0 pixels, okay, why 0 pixel? Because it won't affect the computation. Remember, the convolution operation is just basically the weight times the x, right? So we have, let's say, j, and j. So if anything that is multiplied with 0, although the weight is not zero, is non-zero, since X here, okay, the padding is zero, so then it's just zero. So it won't affect the computation. So that's why. All right. Now, because we have these extra pixels, the padding, right? So as you can see, the output dimension now is no more 3 by 3, but it's a 5 by 5. All right. So of course, with padding, then you will get a larger feature map, right? Larger feature map. So in this case, the input is 5 by 5, right? And the output is 5 by 5. With padding, we have 7 by 7, okay? If we count the padding as well. Okay, now, so I think we have a question. How do we make the filter needed? Is the filter going to be made automatically? Okay, all right. Remember the filter, okay? The filter is just the connections, right? So remember here, that is go back to this one, okay? So we define the region, right? And that region is basically the filter. Okay, the size of the region is determined by the filter size, right? Now the filter size, okay, here is a 3 by 3. So we connect the input, okay, to this unit. So this is the unit of the hidden layer, right? And remember in neural network, so this is the traditional neural network, let's say for example, so this is your X, X1, X2 until XD, right? So this is your unit in the hidden layer. So we have the weights, right? The weights. So this is W1, W2, W3 until WD, right? Now we apply the same principle here. Okay, so we have the weights connecting to this unit, right? All the weights there, okay, associated with the input, right? So the weights are basically just W11, right? Let's say this is the first weight, the first value, W2 until W3, 33. So the collection of the weights are basically the filter, all right? Now in neural network, we're gonna train the network, right? We're gonna train the network. So that means the weights here are gonna be trained, okay? They are gonna be updated by the gradient descent algorithm. So we are not going to define the weights manually, but they are going to be defined automatically by the gradient descent, right? So the gradient descent will determine what is the best features to be extracted. So I hope that answers your question. Okay.
Maybe the question is about how to initialize, doctor. Initialize for the filter value.
Okay. Or you mean the initialization? All right.
Yes.
So we can use random initialization. Okay. When we train the network, of course, we need to have some values, right? The initial values of the weights. So we can use random initialization, or we can use like, you know, the Xavier initialization. So there are a few initialization that we can use, right? In TensorFlow, by default, is a Xavier initialization. Okay, so is that answering the question?
Hopefully it answered the question.
Okay, all right.
Answer it.
Okay, okay. So okay, can I move on? Okay, now, all right. So we have this padding. Okay, all right, and then the stripe. Okay, the stripe. Okay, so stripe is another parameter that you have to consider. All right, so the first one is the filter size or the kernel size. And the second one we discussed just now, padding. Okay, you can set in TensorFlow, it's easy. Okay, it's easier. You can just set it to same, means the output dimension will be the same as the input dimension, or no padding at all. All right, no padding. But you can also define the number of padding that you want. Okay, now the third one is stripe. Okay, stripe. So stripe is the step size as the kernel move to the right and to downward. Okay, horizontally and vertically. Okay, the movement of the filter, or the magnitude. You can think of it like the magnitude of the movement of the filter. Right. Now, in this case, we from here, okay, from here, right? So we move to this region. So that means we skip one column, right? So this is, we are moving to the right. So we skip one column. Okay, we skip one column. So here the stride is equals to 2, right? So if it is equals to 1, then we go to we are not going to skip, we go to the next column. Okay, if this is basically moving to the right. And then after we reach the corner, okay, the right corner of the image, then we're gonna move downward, all right, move downward. So here, as you can see, the stride to the, to the bottom is also 2, okay, 2. So if you set it to 1, then we just go to the next row, okay, next row. So we are not going to skip any row, okay, any row, right? Now stride, of course, as you can see, all right, it will affect the output dimension, okay, the output dimension. So in this case, the input is 5 by 5, right? The filter size is 3 by 3 because the stride is 2, 2, okay? Then we have only just 2 by 2 feature map, 2 by 2 feature map, okay? So you can, so if the stride is greater than 1, if it is greater than 1, still it will reduce the output dimension, okay? But if it is more than 1, it will further scale down the output dimension, right? Okay, now if you have padding, of course, the output dimension will be larger, okay, because of the padding. But still, as you can see, it reduce, okay, further reduce the dimension, the output dimension, right? Okay, so this is stride. Okay, then the last one, okay, the last parameter is depth. Now depth, we have two types of depth. The first one is input depth, and the other one is output depth. Right, so we discuss the input first. Now the input depth is refers to the the number of channels that you have in your input data. So if it is color image, then we have 3 channels, right? We have 3 channels: red, green, and blue. So the depth is 3. So you have to set it to 3, right? If it is 1, if it is a grayscale, then of course it's just 1. Okay, just 1. Now, how we apply the convolution operation, right? Regarding the convolution operation, separate filters are defined for the channels. So each channel will have its own filter, okay, own filter. So in this case, let's say the depth equals to 2. So assuming that, to simplify the the discussion, so we have only 2 channels, for example, let's say. So as you can see, we have two filters, right? 2 filters, right? The convolution operation is the same. Okay, so how we we calculate the convolution is exactly the same, where we perform multiplication between the elements and then we take the sum, right? We take the summation. Okay, now then we're gonna have 2, right? 2 output from the convolution. So we just add them both. Then we get a single output, a single feature map, right? A single feature map. All right. So that is for the input. Okay, input depth. Now the output depth, okay, the output channel refers to the number of feature maps that you want to produce, that we want to produce by the convolution layer, right? So one filter, a single filter, produce a single feature map, okay, in general. So if it is a color image, so although we have separate filters for the channels, still we're gonna have eventually, I mean, like the output is just 1, right? So we have only 1 feature map. Now, so that means we can only extract 1 features, right? So we want to be able to extract as many features as we want. So we can set, okay, by using this, this parameter depth. So the output depth. So if you set it to, let's say 100, D equals to 100, then you're gonna have 100 feature maps, right? 100 feature maps, right? So that means you're gonna define 100 filters if it's a grayscale. So if it is color image, okay, so if it is grayscale, right, grayscale, let's say D equals to 100, then the number of filters, of course, this is representing but the number of filters, right? So you're gonna have 100 filters. So if it is a color image, so let's say depth equals to 100, so you're gonna have 100 feature maps, but the convolution operation, okay, is the number of convolution operation. Yeah, I mean like the number of convolution is by the region, but let's say we equate it to 1, okay, the whole input. All right, so then you're gonna have 3 filters for each, for R, G, and B. So that is only 1 convolution. So then you have 100 feature maps, then you times 3, you times 100. So then you have like 300 filters. Okay, 300 filters. Okay, although the number of feature map is still 100. All right, so that is a color image. So if you're dealing with color image, then the computational requirement is basically times 3, okay, for one convolution layer. Okay, right. So that is the last parameter of convolutional layer, right? Okay, now pooling layer. Okay, so pooling layer is to reduce. Okay, the purpose is just to reduce the size of the feature map. Okay, the output dimension, right? The dimension of the feature map, right? Why we want to reduce it? Okay, why we want to reduce it? Now, remember, if you let us use this example, right? This example. What we want is basically just the feature, right? So that's what we want. That is the information that we want when we apply the convolution, right? On this, on this data. Okay, by using this specific filter, filter 1, right? The rest, the others are irrelevant information, which we should be removing. So how do we remove? By pooling layer, right? So pooling layer. So pooling layer has no trainable parameters or weights. There is no weight, okay? No weights for this, pooling layer. So the pooling layer is just to reduce the dimension of the feature map while retaining the important or essential information, which is the features, right? The features. Now, there are 2 types in general, okay? The common one, 2 pooling operation, average and maximum. Maximum pooling is by calculating by basically, determining the maximum value. So that will be the output of the pooling operation. Now, before that, so there are 2 parameters, okay, for pooling layer. The first one is the pooling size. So this is the pooling size, right? And this is the stripe, okay, the stripes, right? So that's the stripe typically is equals to the the pooling size. So if the pooling size is 2 by 2, then the stripe is also 2 by 2. So that means we're gonna move the step size to the right is 2, downward is also 2. Okay. Now, using these parameters, first we're gonna look at this region, these values of the feature maps, right? 2, 1, 5, 4. Which one is the maximum? The maximum is 5, so that will be the output of the pooling operation. Then we move on to the next pooling area, right? Which is a 2, 2, 5, 7. The maximum is 7, so that will be the output until we cover the whole values. Okay, cover whole values. Right, so that is maximum pooling. So average pooling, okay, the parameters, let's say using the same parameters, a 2 by 2, size is 2 by 2, then we just calculate the average. So the first area is the first value, the first set of values are 2, 1, 5, 4. So what would be the average of these values? Is 3, so that will be the output, right? So this is average pooling, okay, average pooling. So as you can see, okay, by using these parameters, these are the standard, okay, default parameters of in TensorFlow and also in PyTorch, right? Normally we just use a 2 by 2 pooling size and stripe equals to 2 by 2. Okay, so as you can see, by using these parameters, we reduce the dimension by half. We cut it by half, right? From 4 by 4, it becomes 2 by 2. Okay. Okay. Now, putting everything together. Okay, so we discussed the convolution layer, pooling layer, and we know the fully connected layer, right? So that those are the the standard layers that we in neural network. So CNN for image classification is basically just to learn the features, okay, of the input through convolution, okay, and focusing on the the important features by using pooling layer, okay. So we reduce the dimensionality of the feature maps, and of course we have the nonlinearity, all right, the activation function to introduce nonlinearities to the model, and finally we're gonna predict the data using fully connected layer, all right. Okay, now so we have the input, okay. Let's say, okay, we have the data, all right. So when we build the model, the CNN model, we have the convolution layers with activation function, let's say ReLU, okay, rectified linear unit, okay, and then we have the pooling layer to reduce, okay, to reduce the dimension of the feature map, right? So when we perform convolution, so this is the feature map, okay, this is the feature maps one, right? And this is the reduced feature maps, okay, the reduced one, okay, the reduced one by using pooling layer. Then we can always, of course, we can always have many layers of this convolution and pooling, all right? So we add more layers, all right? More layers so that we can have a deep neural network, right? So the second convolution, as you can see, applies on these reduced feature maps. Okay, we apply the convolution on the reduced feature maps, not on the data, not on the input data, but on the reduced feature maps. So here, the first convolution, as you can see, right? The channel, the input depth is depending on the input data, right? So here D equals to 3, right? Here, let's say we produce 100 feature maps, right? So we have 100 feature maps. So the second convolution, the D is, the input depth is 100, right? It's 100. Okay, let's say, we want to produce 200 now, 200 feature maps. So the second convolution produce 200 feature maps, right? And then we have the pooling, okay, pooling. So this is the reduced feature maps, okay, the second feature map, the reduced one, right? Still there are 200, okay, but reduced. Okay, now, so that's the first thing that I want to highlight here. Now, the second thing is that why we apply. Okay, what happened if we apply convolution on the feature map, not on the input data? The first convolution, okay, the first convolution, as you can see, we apply the convolution operation, which is, this convolution should be able to extract features. The first convolution, okay, the features, because it's a raw data, all right, the features could be like edges, some basic primitive features like edges, dots, right? Horizontal line or vertical line and so on, right? So that those are the features that will be extracted by the first convolution. Okay, then coming to the second convolution, we apply convolution on the feature maps. And we know that the feature maps are basic primitive features. They are not the raw data, right? They are not raw, they are some features. Okay, so the second convolution layer, okay, it will produce features by combining these basic primitive features. Okay, so the second convolution layer, the output is a higher level of features. Okay, a higher level of features, or more complex than the first one. Now, as you go deeper, if you have, let's say, 10 convolution layers, right? So, and you keep on performing convolution on the feature maps, then you are basically extracting more complex features. As you go deeper, the features becomes more complex and more complex. So this is like a hierarchical feature extraction. Okay. Now, to give you some ideas, all right. So this is from a paper. Okay, a paper. So the low level features. So this is the actual, all right, a real one, right? So this is a facial recognition, right? So the first figure here on the left, those are the low level features. Okay, so in this paper, they observe what are the features that have been extracted by the model. In the first few layers, as you can see, right, the features are just lines, dots, edges. It could be horizontal lines or vertical line or something like that. Now, when it comes to the middle convolution layers in the middle, right? So the features are some like, structure. It's no more just a basic primitive features, but as you can see here, so they could be eyes, could be nose, mouth, and so on. So it's a combination of the low level features, right? And when it comes to towards the end, okay, the deeper layers, so they are basically just, they are no more just eyes, nose, and mouth, but facial structure. Okay, so they are complex, they're becoming more complex, right? So this is what, CNN can do, okay, by using this, convolution operation. Okay, and eventually, all right, so once we have the high level features, okay, we just give it to the fully connected layers to perform prediction, right, to classify the data into the classes. All right, so so that would be the end of the sharing. So if you have any question, yeah, so or I just pass it to Dr. Lily. Okay.
Okay, thank you, Dr. Halim, for complete and detailed explanation about CNN for image classification. Okay, for everyone that you have a question, you put the question in the chat box, or if you don't mind, you can directly ask the question to Dr. Halim, yeah. Open your mic or just raise your hand. Okay. Okay, I'm still waiting. But before that, I want to ask some question, Doctor.
Okay.
We see here that there are so many hyperparameter that we use in CNN, especially. For example, we can determine how many kernel or filter that we want to use, and then many class convolution layer that we want to put in our architecture, especially if we don't use like a transfer learning. So based on your experience, how you doing the hyperparameter tuning? Because there are so many, or usually student always like doing some hyperparameter like a brute force. They just tuning some parameters that they remember or they want to tuning. So based on experience, how the step we can hyperparameter tuning, Doctor?
Okay. Okay. Interesting question. Okay, so this is based on my experience, all right? First, is from the literature. Okay, so because normally, all right, the filter size is 3x3. So normally we just, this is if we are talking about if you build your own CNN models, right? So normally we just, normally what I will do is just use the common parameters from the literature, which is a 3x3, or 5x5 or 7x7. I never go beyond 7x7, all right? And the number of layers also based on the literature, but normally I would say it's better to have more than 5 or 5 and above, right? So if it is just 3 layers of convolution, then we can think of it like, the features that will be extracted is not complex enough, sufficient enough. All right, so it's better to go beyond that. But then of course, it depends on the resource that you have. If you have GPU, of course, you can go beyond that. All right. So basically, in general, Okay, the parameters are set based on your experience reading, basically in my case, based on the literature. Okay, so if you the easiest one is just to you, like Dr. Lily mentioned just now, use transfer learning. So transfer learning, you don't have to build the model. All right, so you can just use existing one, then you don't have to change the parameters. Okay, and for transfer learning, normally we just remove the output layer. Okay, and then we replace with our own output layer. So that's all. You don't have to worry about the parameters. Okay. Regarding the training parameters, like learning rate, or if you want to use non-penalties and so on, or dropout rate and so on. Okay. So normally I would just use the for image classification. So I would say use the default value. If it is not okay, the default value in TensorFlow is 0.001. Okay. If it is not okay, then you can reduce it to 0.0001, right? So normally, based on my experience, text data or computer vision, a lower value is better. Based on my experience. For time series data, because it's not that as complex as image data, 0.001 is okay. But if you want, you can reduce it. Yeah. So I'm not sure whether it's too many answers there. Okay, but in general, basically it's based on experience and also based on your reading. Yeah. Brute force is one. I mean, you can try one by one, but then if you are dealing with image data or video, then it's almost impossible to brute force. Okay, right.
Thank you, Dr.
So yeah.
Especially maybe some of the students like they used to using grid search in machine learning. But
Yeah.
I mention I remind them that using grid search it's not effective if you use a deep learning, because you have to wait for a long time
Yeah. Yes, that's true.
for your hyperparameter tuning, right? And we
Yeah,
don't
yeah.
have a good one.
Mm-hmm.
Okay, maybe continue for the transfer learning, Doctor. We have so many architecture, right, in the transfer learning, and based on what you have done or your experience, how you choose for the transfer learning, which one is you will choose first, because we
You mean
have
the model? You mean the model?
the model, transfer learning model,
Okay.
PGG.
To be honest, normally I would just use ResNet or DenseNet. So is VGG 16, although is good, but then for me, I think VGG 16 is, based on my experience, is more difficult to train because there is no residual connection. Okay, so normally I would just straight away use ResNet. Okay, which is if you refer to the to the literature, many researchers they just use they use this ResNet or DenseNet. Yeah. So, and it has been proven that ResNet or DenseNet is capable of solving most of the problems. Yeah, I mean like research, but for for industrial problem, I had last time I had one project with Dyson. So we use ResNet. Okay, we use ResNet 3 models. We perform transfer learning on 3 models: ResNet 50, ResNet 101, and ResNet 150. And the outcome is that the models able to solve that problem. Okay, the problem is basically to detect defect detection in their prototype. So we want to localize the defect. Where is the defect? And also we want to perform segmentation on the defect, the shape of the defect. So so based on that, ResNet is capable of solving that problem. Yeah. So we just proceed with ResNet. Yeah.
Because if we see the state of the art, Doctor.
Yeah. Mhm.
new algorithm, new model,
Yeah.
but definitely the number of parameter I think increasing
Yeah. Yeah.
exponentially, yeah, for
Yeah.
the
Yeah. Yes. Yes. That's true. Yeah. That's
so
true.
that's because of that it's quite difficult to give advice to students. Usually they like want to have like the new one, the newest one, but I have to see your infrastructure.
Yeah. Yeah. So is sufficient. I mean, like, yeah. If we just if we refer to the literature, then there are many models coming out. Being proposed by the research group, researchers, or even industry. But I would say ResNet is sufficient. I mean, like based on my experience, it's sufficient for computer vision as a backbone. Because normally if you want to normally we'll add our own layers after after ResNet. ResNet is just as a backbone, and then we add our own layers, we modify the model. Yeah. So for feature extraction, ResNet as a backbone is sufficient, or DenseNet. Yeah. Mhm.
Yeah, there's maybe I also have tried EfficientNet, the one that
Yeah. EfficientNet.
the newest one, and I think the number of parameter not as high as the
Yeah.
ResNet.
Yeah. Yeah. That's true. Yeah. EfficientNet. Yeah. That one is also good model. Another one is MobileNet. MobileNet also the number of parameters is not as many as ResNet. Yeah. So
So
these two, EfficientNet, MobileNet, is good for mobile application. Yeah. If you want to embed in the mobile application, mobile apps, something like that. Yeah.
I see. Okay, thank you, Doctor,
Mhm.
for the explanation. Okay, for the students, you have a question, feel free to drop your question in the chat box, or someone want to raise your hand, or I want to ask you, yeah, exam. If you don't have a question, so the lecturer will ask you.
uh, yeah, okay. So I think that's one. What are some tools used in deep learning other than code editor? You mean the library, or okay? So basically in general, right? The tools, of course, as you know, Python is the currently the most popular programming language for data science and machine learning. So I would suggest to use Python with either TensorFlow or PyTorch. Um, PyTorch is more popular in research among researchers. TensorFlow, based on my experience, the industry prefer TensorFlow more. I think because of the ecosystem, the support is much better than PyTorch. For example, let's say if you want to deploy in a mobile application, so there is a TensorFlow Lite. So TensorFlow is more popular. All right. So that's about the programming language and also the library. The tools, I mean, like the editor. Okay, the software. You can use either Jupyter Notebook. I think Jupyter Notebook is very popular among the researchers, as well as the students working for their final year project. But if you want to have not a web-based, because Jupyter Notebook is a web-based application, web-based software, you can use something like PyCharm or Spider. Spider is, I'm not sure, is it something like the spelling is like this, Spider or PyCharm.
Usually, if you have
Yeah,
Anaconda, you will have spider in it.
yeah. So if you install, if you use Anaconda, then normally you will have this Spider, right? And Jupyter Notebook. So that's about the tools. Yeah. So I hope that answer your question, Stanley.
Maybe no question, Doctor. Is I curious. Usually in university, because in computer vision training, usually we need GPU. So usually
Mhm.
you will your own physical GPU, or you just use like a web or cloud-based GPU.
Okay. In our school we have the physical GPU server. But then that GPU server is not it's not like as powerful as the one that being used by OpenAI, or even like maybe Intel. So we have A40 GPU server. It's quite old, but then that GPU server is, it's sufficient for doing, to perform experiments because it has I think 48 gig of memory, not the CPU, but the RAM, the GPU memory is a 48 gig. Right. So we have a smaller one, smaller GPU servers with 3090 RTX 3090. We have two GPU server, and then we have a even smaller one like 2090. So it depends on the requirement. So if let's say the students they work on a computer vision application, then so we assign them to use the powerful one, the A40 or 3090. But if they are working on like signals or time series data, then they can use the 2090. Yeah. So we have one A100, but then I'm not sure. I don't have that access. A100 is a little bit better than, A40, but that's the only one that we have. We don't have like, the newer one. The newer one is more powerful. Like, they have a Tensor CPU, something like that. I'm not sure. Can. But cloud, I think is okay. Cloud. Some students they pay on their own. Because they don't want to wait, because if they want to use the physical one, they have to wait.
Yeah.
So they just buy their own cloud, GPU.
You stay in Google Colab, yeah, Doctor.
Yeah, Google Colab. Yeah, normally they just use Google Colab and they pay credit. They buy some credits to use the GPU. Yeah. Mhm.
It's like similar in some of the student here.
Oh, I see.
Mhm.
Okay.
Some of physics, I'm not sure about the detail of the GPU, but yeah, we have the like a waiting list.
Yeah. So that's the drawback of the GPU, physical GPU server. So they have to wait. Yeah.
Okay, thank you, Doctor.
Okay.
Okay, another question from the students. Okay, maybe last question from me lah ya. If you
Okay.
question from okay, usually Doctor, if we want, we try to training our image for image classification. We have tuned some hyperparameter, and we don't know. It's like our performance is like trapped in the local optimum. So, what's your suggestion? What we need to do? What we have to check if we have changed the learning rate? Try some of the others hyperparameter tuning. Maybe
Okay.
can face this one, yeah.
Yeah.
Or their final order.
Okay. So when we train the model, all right, so we have the validation set, right? So we have the training set and the validation set. So when you train the model, we have to observe both the training loss and also the validation loss. Or if you want, you can use training accuracy and validation accuracy. So if you notice that the validation loss, for example, let's say start to increase, okay, normally it should be decreasing, okay, but after certain epochs, let's say or 100 epoch, after certain epoch, certain number of epoch, when the validation loss increasing, then we know that it is an overfitting. So we should stop. So that means at that point is basically the best model, the best parameter that we can have. But of course, normally we don't just train once. Okay, so we try to train the second time or even the third time if you have the resource. Okay, so you should train the next model, the second model using also the same thing. We observe, you know, the validation loss and also the training loss. So it might be the second model, the validation loss is lower than the first one. So that means, you know, this parameter, this, you know, this hyperparameters is better. The second hyperparameters is better than the first one. So that's basically the normally the, you know, the procedures or the, you know, the way or the steps that we use. We have to train several models, okay, because yeah, it's also suggested in the no free lunch theorem, okay, so where there is no single model or algorithm will always give us the best one. Yeah, so we should try different parameters. Yeah. Mm.
I see. Thank you, Doctor. So it's become
Mm.
impact for the student here, yeah, that you need to try some of the hyperparameter. I mean that if your model is not good, I mean it's not the end. So you have
Yeah,
to
yeah, that's true. That's true, Dr. Lily. Yeah.
usually like a student because they waiting so long for the training and then the performance is not good. They like a frustrated, what happened with my model?
That's not the end of the world.
I mean, all of the researchers in computer vision, I think, face it. So
Yeah.
on the right track.
Yeah, yeah.
Okay. Okay, Doctor,
Okay.
thank you so much for the answer and the explanation. So I think we are in the end of our session. I will close it with some summary from your presentation. First one, that image has a spatial structure where fully connected layer usually cannot capture it effectively. Because of that, we need a convolutional neural network. So in the CNN, we have some element like a convolution, pooling layer, and fully connected layer, where in convolution, there are some element like stride, padding, and also yeah, the stride, yeah. So we know how we will assign for each of our convolution process. And the last one, CNN is a hierarchical feature extraction that can be used for our classification, especially in image. Okay, that's all for today. Thank you very much, Dr. Muhammad Halim Muhammad Nur. I give back to Bu Ajeng ya. Thank you.
Yeah, thank you, Dr. Lily. And thank you, Dr. Helen, for your sharing today. Hopefully, all the students who is interested to explore more about the deep learning and image classification can get more knowledge.
Yeah.
So, before we end our session, we will have like the group photo with Dr. Halim and Dr. Lily. So, all students, please turn on your camera so we can have the group photo. Okay, we will waiting. Don't be shy.
Yes,
Turn
yeah.
on your camera. Turn on your camera so we can have the group photo. Yes, some of the students has already turned on their camera. I will take the screen. 1, 2, 3. And the others, 1, 2, 3. Okay. Thank you so much, Dr.
Okay.
Halim, for your sharings today. Hopefully, we can collaborate again.
Sure, yeah.
Yeah, later on. And thank you so much, Dr. Lily, for
Okay.
helping as the moderator.
So,
Uh,
Dr. Lily or Dr. Ajeng, can you
yes.
share the screen capture, the photo just now?
Yes, I
Yeah.
will share it to you.
Okay, sure. Okay,
Okay.
thanks.
Thank you, Dr. Halim.
Thank you. Bye-bye. Assalamualaikum.
Bye. Waalaikumsalam. And then all students, thank you for attending. I've already shared the exit ticket. You can fill in the form. And then after this one, we have another seminar at 11 o'clock. So don't forget to join.
Okay, thank you everyone. See you in another seminar. Thank you, Bu Ajeng.
Thank you, Bu Lili. Untuk teman-teman yang udah isi exit ticket, boleh ya join untuk ke next seminar kita, terutama teman-teman B26 yang sedang mengambil kelas research method. Thank you. Oke, thank you ya teman-teman atas kehadirannya pada pagi hari ini. Saya izin untuk end meetingnya. See you in another seminar. Bye-bye.